Okay, thank you, Dr. Guan, for the talk. And sorry, no time for joining, but I guess you can reach them in the coffee break. And our next speaker will be Professor Helge Wurdemann from University College London. His talk is about shaping future applications with safe and controllable robotics. Please.
Thank you very much for the invitation to this great workshop for all the organizers. And I'm very pleased to be here at IRIS 2025. And today I want to talk about shaping future applications with stiffness controllable robotics. What you see in the background of my cover slide is in fact what many people refer to as the stiff lock manipulator. That was the beginning of the collaboration I had with Kaspar Althofer, who was the coordinator of the EU project, which was called StiffLock, and collaborating with Professor Ariana Manchassi from SSSA, who were in fact responsible for developing the technology during that time. That was about almost 14 years ago. And the manipulator itself is made out of a silicon type body. There are different type of silicons that the manipulator is made of, and there are chambers that are fiber reinforced, and they can be pressurized to achieve bending and elongation. And most importantly is that this is a surgical tool aimed at a minimally invasive surgery. So there's an inner shaft that is free, a lumen that is free, and so you can push through instruments, and in our case, we pushed through a coax tool and also an endoscopic camera. At that time, we managed to miniaturize the manipulator down to about just less than 15 millimeters, 14.5 millimeters in size, to push it through a port which is commercially available for minimally invasive surgery. And over the years, from 2015-16, we've been working extensively to optimize the design and the manufacturing process to then scale it down, also in collaboration with Ariana Manchassi, to now about 7.5 millimeters that you can see here. And this is then a 2-segment manipulator, as you can see here, fully integrated, and still there's an inner shaft where we can push through some of these instruments that I mentioned earlier on. What I would like to bring to your attention is a publication that is just accepted last week, and this publication, contains a MATLAB toolbox to design your reinforced soft robot based on material and geometric properties. And this was done by Dr. Jialei Shi, who is now a postdoc in the Hamlin Center at Imperial College London. And if you want to have a first glance, you can just scan the code and email either me or Jialei Shi to get access to the MATLAB toolbox. It's not yet on the MATLAB website available, but on GitHub you can have access and play around with it a little bit. But today I want to talk about 2 different applications for soft or stiffness controllable robotics, and one is in the field of healthcare engineering and the other one in collaborative robots. So these are 2 projects that are led by Xin VP and Dr. Wenlong Gao Zhang, who has been previously in my lab. So the first project concerns how to harvest vessels from the leg to perform then coronary artery bypass grafting. So this is a disease where the arteries in the heart, they are blocked, and you can of course do a minimally invasive intervention and deploy stents into these vessels to open them again. But in some cases, you need to completely replace them. And for this procedure, what is required is vessel harvesting. And one of the areas where surgeons would harvest these vessels are legs. So they go in with a tool like this, and they deploy it, they make a small incision, and then they remove the surrounding tissue from the vessels. And there are many branches, of course, along the vessel, as you can see here. And these ones are then separated. So in the end, you have a vessel, and the vessel will be then tested if it's still healthy. And then at the same time, they will then suture it into the heart. So there are some constraints. And one of the main constraints is that when you do this procedure, the surrounding fat layer around the vessel is completely removed. And this is very important because when it comes to integrating it back into around the heart, it would be good, and studies show that it would be good that the vessel, the fat layers are protecting the vessels around here. So what we have here developed, and the patent is pending here, is a drawing robot that is working in the other way than the conventional eversion robot. So whereas we have standard eversion robots, the material from the inner channel is fed and inverted at the tip to allow growth. And we have seen many different applications. For example, in colonoscopy, there are some projects around. But what we have done here is we have built an eversion or inversion robot, we call it inverter, where the material is fed from the outside and then inverted to the inside, so that you have frictionless movement of the robot and can encapsulate any environment inside. And we believe that this is one method to protect the fat layer around the vessel. So now we have built a first prototype. The first prototype has a base. The base includes the crimped outer layer of the outer sleeve that you need to then feed through a rolling mechanism. And the entire chamber inside is sealed so that any pressure is acting on the tip and pulling through this roller mechanism, the crimped material to allow the robot to grow. So Xin-Yi will also present this as part of a session tomorrow, in the soft robotic session. And here you can see how the robot is moving freely. And then we have built a number of phantoms, vessel phantoms. One of them is a rigid 3D printed phantom, and the other one is a phantom vessel, which is soft and very similar to the properties of a vessel, to demonstrate the feasibility of this. So if you are coming to the session tomorrow, please approach Xin-Yi, who is with us today as well, to discuss her results. On the other side, I would like to introduce Wen's long work in building the next generation of collaborative robots. And I really enjoyed the previous talk from EPFL about their robot and their application areas, for example, in human-robot collaboration. This started with a project called 4x3, H2020 European project, where we built a new generation of adaptable and reconfigurable collaborative robots. And the idea was there to build, in the first instance, stiffness controllable or variable stiffness links. So we have the sleeve that is made out of some fabric, mesh, and silicon material, and we pressurize this, very similar to a tube or to a car tire. And so we can change the stiffness inside depending and proportional to the pressure inside these links. And the nice thing about these variable stiffness links is that it allows to generate omnidirectional stiffness. So stiffness from any direction, as you can see nicely here. So that was the very first version in our lab back then at King's College London, where we used standard servo motors, and in between these standard servo motors, we integrated these variable stiffness links to demonstrate the feasibility of this approach. So from there, Wen Long took it back a step further, and he developed stiffness controllable bending actuators that generate stiffness controllability through the antagonistic behavior. So very similar to what we've seen in the presentation before from the so antagonistic behavior is that you have two different forces that oppose each other, and you can either actuate one or the other side to generate bending, and if you pressurize both of them opposing each other's forces, you can generate not only bending but also stiffness variability. So this is what you see nicely here. So we have, two chambers, and these chambers can be pressurized using any fluid. We use air pressurization, and then we have a hinge integrated in the middle, and if you pressure one side or the other side, you achieve bending, and if you pressurize both of these chambers, you can achieve either, if there's a difference, bending and stiffness variability. So with these prototypes, Wen Long has compared this to different units, joint linked units. So here you can see a 3D printed stiff joint, and here you can see the variable stiffness joint. Both of them have a servo motor, and here you have again the same configuration, but in this case you have our variable stiffness bending joint. And you can see here nicely how you can modulate the stiffness using different type of joint link units. So now we have taken this approach to a different level, and Wen Long has produced a modular variable stiffness family. So you can see here these different joints. So we have a bending joint that I explained earlier on, and we have a variable stiffness joint, and then we have also a rotational joint here, and all of them are based on antagonistic stiffness modulation. And in order to allow modularity, we have generated these connecting plates. So you can choose, according to your application, a series of different bending, rotational, or link components. And here you see them again. So we have here the bending joint, and you see the two plates, adapters. So these are adaptable to the variable stiffness link and also to the rotational joint. And you can see nicely the integrated pipes that can then forward the pressure and supply the pressure to the next few components. And here we have done modeling and simulation for each of these links, and then also for the overall manipulator. And we had two applications in mind, one in healthcare. So for example, feeding patients using a series of different components. And at the same time, we looked into manufacturing and working on different tools when you have bimanual movements. And here you can see nicely how one of these robots is assembled. So you have here the bending joint, then you have a rotational joint. You just need to fix them into position. And once you have designed your entire robot, you can use a MATLAB toolbox to understand the workspace and the stiffness modulation. And then you can also understand from internal sensors the pressure that is acting on these different components. So with that, I'd like to leave some time for questions and answers. And I thank very much you for listening to my talk. Thank you very much.
Thank you very much for Professor Wurdeman's talk. Now, any question for his excellent talk about the safe phase control? Okay, maybe one. I have a question because I see that most of your research is about surgery or healthcare. Most of them are about human care and medicine. Do you see any possible to apply this kind of technology outside the medicine and the healthcare things?
Yes, so first of all, the history behind the healthcare application is for sure the collaboration with SSSA and Ariadne Chassi in stiff lock that had application in the field of medicine. At UCL, we have 8 affiliated hospitals, so there is a direct link to any clinicians with different applications in medicine or in the healthcare sector. And we are looking also into other applications, for example, inspection, nuclear decommissioning is a very hot topic in the UK at the moment. But you can see also some application in human-robot collaboration, so building new devices that can safely work in close collaboration and interaction and physical interaction with the human. And then there are also ideas of deploying some of these actuators into vehicles to inform drivers to take back control and go even beyond just guidance, but also then to augment drivers to react appropriately in certain situations. Yes.
Okay. Maybe we can just. Okay, thank you. So we have time for one more question. Any question? Yeah, please. Please.
Hello, Professor. And I have a question about the optimization. I just wonder how can the co-optimization of steepness schedules and trajectories be formulated for some steep controllable robots when we do some task specific constraint subjects about such as the upper bound on the contact forces, minimum energy expenditure, or the time optimity.
Okay, that's a very interesting question. Thank you very much.
Thank you.
And I think when it comes to soft and stiffness controllable robots, and in many applications, you want to leverage the advantages of soft material robots, which is that you have a certain compliance at the tip. You can also optimize these robots for precision. I think that is also doable, and it really depends on the application. And with respect to understanding or trying to prevent going beyond a certain force that you exert to the environment, I think these types of robots are made for this because through, for example, our design toolbox that I presented at the very beginning, you can constrain these forces, and then you can manufacture a robot and use materials for that robot that would not even allow you to go beyond these interaction forces.
Thank you very much. Thanks.
Okay. Thanks, Professor Wurdemann, for your talk and your answer. Thank you.